basics. I gave you an overall idea. Does anybody have any doubt out of your curiosity how this technology is moving, how it has evolved? Anything that comes to your mind, you have any query, you can ask me before we start.
Ma'am, I was having one curiosity.
Bolo.
Ma'am, how are we able to how are we able to reduce the size of the MOSFETs?
Okay, very good question. Nice. And another good news, you see, as you know, our country is like developing very rapidly, but we were lagging in one thing. Before I answer your question, let me share. We were lagging in chip fabrication, and it was limited, to USA, European countries, and then Taiwan, and then China. The China had a very strong policy, government gave subsidy, and this manufacturing of a chip, it needs millions and trillions of dollars of investment. And as you can understand, this investment, first of all, how the government have been, working and the way the system is. But now with Modi, he has initiated all this, and now the focus is on chip making and startups related to that. So there is already a big boom in VLSI. We are making of a chip, that area is known as VLSI. Okay, very large scale integrated circuit or microelectronics. Micro means, now 10⁻⁻⁶, and we are making transistor. What is your good name? You asked me question.
Sorry, ma'am, can you please repeat the question?
Your good name.
Tarang.
Tarang asked me question, right? So MOSFET is the device that you make in the chip, and it is of the dimension of micrometer. Now let me give you a very simple example that everybody knows of cheese, right? If you make cheese smaller, if you are given a chunk of a cheese and then asked to taste, you will taste like cheese, like, okay, cheesy. Then you will make it half, and again somebody asks you to taste. Still, it will taste the same, right?
Yes, taste will not change.
Again, you make it half. It will not change. So here, the point is that when you make things mechanical, when you have mechanical parts, right? If you scale down is a challenge because it may not perform the way it is. But when you are given a material, a chunk of a material, and you make it, the material property still remains the same. Okay, it is the material property. So material science comes into that, and the property gold, if you make it smaller, it will still remain gold. So here it is basically silicon. Silicon is the material on which we make the transistor. Okay, and there are different, like, in diode you have cathode, anode. Yes, you will have terminals and it works, but it is material there. And if you make it smaller and smaller, still the property will preserve the property, right? The current will flow, but the current will now be less in magnitude. Okay, so kam ho jayega thoda current, but still it will work as a circuit. It will process your information, and that's whatever we need the current, we will make it, we will fabricate accordingly only. Okay, तो ऐसा नहीं कि current बिल्कुल कम हो जाएगा और die हो जाएगा. It is still enough to make the circuit. And then with shrinking, when you make the transistor small, right? Now let's say if you have a smaller room and it has opposite doors or the opposite windows, and if you have to cross that or a smaller road, it will take less time. So the signal that has to pass through a smaller transistor will take less time. So the delay is reduced, the bandwidth is increased. Okay, when you reduce the delay, then the bandwidth also increases, so it can work with higher frequencies. And the other thing is less power. I mean, now a chota room hai, so a smaller bulb may be enough. If you have a bigger room, you will need, so a smaller circuit will need less power because chota sab hai. So there is an advantage by it is not only size that you can carry in your pocket, but every way it's a win-win position. So I hope you have understood what I said, right, Taral?
Yes, ma'am. Yes, ma'am.
Yeah, so then you, if you are interested, as I said, this is the future, and the future of after this electronics, as I said, this MOSFET has been shrinking, but now there are problems because it's just few atoms, and this shrinking is possible because we are see, one is there is a research going on circuit side, but another research also on fabrication side that you should be able to fabricate those small things. So as those technology also advances, we are able to get smaller and smaller. In one day, we cannot reduce, too much, right? But what are you telling me? Somebody said something. I could, ma'am, could you please reshare the screen? I think I have. Okay, I'll reshare. I get your point. Uh, I'll keep my PPT also open, and I'm sharing my entire screen only, and let my PPT be open. So everybody can see the screen.
Yes.
Yes,
Okay.
ma'am.
Okay, good, good. So, what? Where was I? Yeah. So, simultaneously, like, if you want to make a little puri and then smaller than that, smaller, you should have those, to make that also. For example, so you need to have manufacturing facility, and that is where the cost comes, right? And you should be able to make smaller and smaller, and that is the challenge. We are not nature that we will make one atom, and atom में से molecule बना और उसमें से, so that's how this life came into existence, right? So, but that's what is the goal. Right now, what we are making is like a sculpture. कि भाई stone है and then you carve it down, right? So it's that way. But and that is expensive. It results in pollution, and I mean, so if we can make it in a clean way, like what the nature does, right, there won't be any waste. So all this technology that we are developing also, we have to make sure that it is green. And I mean, if you can make it atom wise, you building. So that's the goal. The final goal is that we make it like we work like a nature. That there will be nano machines that will bring atoms together, and it will create a molecule, and then from that you get the chip that you want or anything in future. So this is what in future we want to make. We want to bring atoms together, and such machines, these tiny robots or nano machines, you will need them in thousands that can do this kind of job. So these are the future things. As I said, MOSFET is encountering red brick wall, and the future is nano electronics. And the beauty of nanoelectronics is that nano transistors are there, like single electron transistor. If you make it more and more smaller, the smaller you make, the performance will get better. So that's the beauty. And it works on a different physics. It works on quantum mechanics. And that is really, really hard to understand, okay, initially. So it is how the nature works. It is how one atom works and electron works. Quantum, if you want to understand how electron behaves, how atom behaves, or how universe behaves, you have to get into quantum mechanics. And that's the stream. That's how the nature works. And if you know the word spirituality, right, so that is nanotechnology, nanoscience. And then when we apply to electronics, it is nanoelectronics. If you, our religion is, our Hindu religion is based on science, and it's how you get spiritual. The goal of the life is spirituality. But this religion, that is spirituality, I mean, religion means not the way we perform every day. So spirituality and science, they meet at one point. Okay, so all these things are connected. Anyway, I spoke something more than what you asked. I hope it was interesting, right?
Yes, ma'am. Yes, ma'am. It was very interesting.
Correct, correct. So you can ask me. I also love to answer such questions. So, and if you don't know answer, it's okay, but you should have questions. That's what I believe. Okay. Okay. So with that note, let us start ahead with our and then lab. We will start from the next one, and we'll start with the diode so that you are all comfortable. And then by the time we will see, initial lectures may seem to be easy. Okay, but you have to understand the concept, and that's what will be asked in your exam. And if you want to get A grade, copying will not help you. I mean, although the platform doesn't support, but anyway, if somebody is like, given the chance, anybody will be tempted to. So just understand and do your things. And it has happened also, students may share some results and they are caught or maybe done from the website and copy pasted. So I mean, just understand, and even the way I set the paper is the one who it is filtering, like, okay, if I give one day, whole class will answer, but in that limited time to answer the questions efficiently is directly proportional to how much genuinely you know. Okay, so if your goal is in my class, anybody can get A grade provided you have understood, and that understanding comes from your regular attendance. Okay, you are all capable of doing anything. So with that, the quality of the student and your caliber, I am talking that anybody can get A grade. Okay. So the students are smart, the faculty is smart, so everybody is capable. Now, how you use your capability is up to you. Okay, so with that thing, now let us to understand. We'll start with the diode and any device, and even in your life, understanding is the main thing. So you understand the concept, you understand the physics. Understanding here means it is the physics, and your electronics is based on the physics. And when I say physics, it is also material science, chemistry, all those things comes into that. Okay, but to make a circuit, you have to understand this first. Otherwise, you cannot make it an efficient circuit, and then throwing something that you develop an application has no sense. As an engineer, we are looking for optimization, long lasting life, everything. So now, as you know, we are talking of diode, and the meaning of diode is di is two, and two electrodes, the device that has two electrodes. And what are these two electrodes? It is P and N. Okay, so P type, N type, you have a semiconductor which are it's not that you will glue these two slabs, you will sit down and you will glue it, right? There are semiconductor foundries, I was just talking to you, and there are ways of making, but it is at the end P type semiconductor, N type semiconductor bought together, right? And you know what is N type, what is P type. Now semiconductor, we discussed last time. Why semiconductor? Because we want a control, we want to on and off. ऐसा नहीं कि ऑफ करो तो भी चलता रहे या चले ही नहीं. Insulator will never pass a current. So that control is main thing anywhere you are, right? Control of mind, whatever. So control of speech. So control is main thing in device also. It's all about control, and we should be efficiently be able to control, and that's why we stick to semiconductor. But now in semiconductor too, because now in the electronics it's a game of current and voltage. What we want at the end of the day, whether it is your life or your device, we need more current, because current is the main thing that is processing, that is passing your information. Okay, so like you need more interest of your money, so more return. So similarly, that less input, so less input voltage, thoda bhi voltage input ho to zyada current milna chahiye. That's the measure of the goodness of the device, right? So everywhere you say this human being is like this device also has a characteristics that is known as IV curve. Uska nature kaisa hai device ka, and for giving this much of voltage, it will give this much current. So that's what we are looking for. So everything has to be at the right time with all right conditions and the right characteristics. We make an application. So here N type is, so we need now conductivity in a semiconductor more than what it can offer, right? As I said, we want more current, kaise milega, more conductivity. Current can be because of the hole, because of the electron. Here in the diode, you have flow of both electron and hole. Okay, and they both are moving, and we'll see how, and then it is creating a current. Now you have N type. N type is a pentavalent impurity, means for example, phosphorus. When added in some amount, you will get this kind of lattice structure. Uh, Right, so this is just a pictorial representation of the lattice structure when you have a pentavalent impurity like phosphorus, and it will add an extra electron which will create current. Okay, mobility. So current is not, if the electron is resting there, it is not a current. It has to be mobile. It has to move, right? And then when electron is moving, it creates a current, but you need more the electrons, more the current. And for that, in the N type is added with a pentavalent impurity. And the deficiency of an electron is an hole, and that can also create a current. So here also we in the P type, you have trivalent impurity, for example, boron, which is a deficiency of the hole. So given a little energy, now that energy can be, you can heat it also, you can give a temperature also, right? And it will break the bond. It will break the bond. So when you heat it also, let's say it will break the bond and it will be replaced. So that's how also, and then consequently, this hole will propagate. Okay, and similarly for the electrons also. So, and the another way in electronics, how do you give the energy? It is a voltage. Voltage is nothing but a potential and energy that the electron gets. Okay, in a normal temperature, right? We don't heat to get a current, right? Otherwise, it will destroy at some point. So this is just I'm explaining you P type and type, and now we are bringing this together. And when you club it, okay, when you club this P type and N type, and then remember, there is for now there is no voltage. This is known positive terminal is known as the anode. This is known as the cathode. Okay, so PA is positive. Always you remember that way, then other you will be automatically able to, so don't get confused. So P and N, and then we make a terminal, a metal contact, so that you make a terminal, it can be connected to the external world. We cannot, if you just leave it like that way, how will you make a so this is a contact here, is a metal contact we make. So we are bringing together. Now when you bring together, some physics happens. Okay, and you have studied this or no, this slide, this P and N. Now we are bringing together. Okay, and we are not giving any voltage yet. No battery right now, only diode is there. So have you studied diode physics? Hello, am I audible, or I am lost the connection?
Yes, ma'am, audible. Audible.
Okay, if you don't have any background charge, one of you can keep your mic unmute so that you can respond to me. I cannot see what is going on because I am with the slide. So, tell me just, I would like to know, in your 12th, 11th, or in your first year, have you studied the physics?
Yes, ma'am. In high school, we have chapter.
Okay, anybody would like to try, or you have forgotten? Then I can go ahead and I'll explain you in a very easy way that you never forget. First year में पढ़ा था क्या diode?
No, ma'am.
No, not in
Okay,
first
no.
year in high school.
Oh, तो फर्स्ट ईयर में डायोड नहीं पढ़ा है इलेक्ट्रॉनिक्स, बेसिक इलेक्ट्रॉनिक्स में?
No, ma'am. No, ma'am.
We had not studied the physics of the diode, only at an abstract level we had studied.
Oh, अच्छा अच्छा, ठीक है, no problem. See, I'll teach you in a way you never forget. And these are all basics. Okay, as an ICT engineer, you should know that how things are working and what will be the future. And these are the basic things that can be, these are basic physics principles that is applied everywhere. But here, especially with this device. So now, as you can understand that, let me go here one back, and you can understand this is P type, it is rich with holes, you agree? And this is N type, it is rich with electrons. And now we are bringing this together. So now what is happening, as you know, that water flows from higher volume to lower volume. And these are mobile, okay, electrons, free electrons, as you can understand. And then this holes. Now when you bring this together, here is an excess of electron, here it is an excess of hole. So electrons will move. Here it is a high concentration of electron, here high concentration of holes. So from higher concentration, they will move to lower concentration. So P will move from this P type to this here, and these guys will move from here to here. And when they are moving, okay, from here to here, then what happens here, right? They will, so these are holes, P type reaching, okay, P type holes as shown here. And then they will recombine. So holes and electrons will recombine, and that is known as recombination. Again, it will neutralize it. Okay, so initially there are recombinations at this surface, at this intersection of this both P type and N type material. So what does it? So recombination happens, and this recombination process, it will result in disappearance of the sum of the free electrons from the N type material. Okay, and then so this here recombination, then it will neutralize it initially. Okay, and thus some of the bound positive charge will no longer be what so there is a that is bound and unbound charge. So some of the bound positive charge will no longer be neutralized by the free electrons, and this charge are said to be uncovered. So initially, this is moving here, this is moving here, they will combine. And we say that these are boundaries. But once they have recombined, then after that, okay, so that there will not be any recombination. It means it is neutralizing. So there is no positive negative charge initially. They get together and they neutralize. But then at this surface, some of this from here, okay, which have not neutralized, they will go this side and these guys will come this side. And this charge is they are uncovered, means they are negative and here it is positive. And now because of this, now see, these are charges, they have electric field. Positive will have little positive electric field, negative will have, and this is the process is known as diffusion. Because of diffusion, after recombination, right, some will this negative charge will appear here, positive will appear here, and then these are electric field, little electric field. When you combine, right, it will have some potential. So this is positive and this is negative. And when this potential is enough, that it is strong enough that it will not allow any more to diffuse. Okay, so it will not allow any more to diffuse, because now this is like a little electric field is established, because these all are electric fields. And when you make it, this is positive charge, this is negative, and this has some potential now. So positive, the electric field is from positive to negative. So this way the electric field is established, and we say that this region is depleted of the original charge, and this is known as depletion region. And the potential, the electric potential that it has is 0.7 volt for silicon. If this was a germanium, it will be around 0.3 volt. And remember, we have not applied any charge. So now this barrier is enough that it will not allow any further electrons to pass from here or holes to pass from there. You understand my point? And only very few, even if it is, will make it. Do you understand this? Or may I repeat again? See, yes, initially, this is holes, this is rich with electrons. Initially, they will recombine. But after that, also, there are some charges that are left uncovered, we say. So this negative will be here on this whole side and positive here. It is physics. That it will diffuse only. We cannot control that. So that is how the nature works. That is the physics, and this will develop a potential and electric field. The electric field direction is from this positive to negative, and it has a potential of around 7.7 volt for silicon, and it is strong enough if the electron wants, if you want a current, and if the electron has you want a current, that electron will move from here to here, and let's say holes will move from here to here, right? So when the direction of the convention is the opposite of the direction, current direction is the convention is it is opposite of the electron direction. So electrons are moving from here to here, right? So if the electrons are moving from here to here, if the electrons are moving from here to here, then your current direction is this direction, right? So that's what you already know that. So the point here is yeah. So if you want a current because of this, if you want a current, that is electrons to move, it has to overcome this potential. Okay, and with no voltage applied, it can't overcome. So the first thing is that there is a diffuse. Now it is this wall. It is like a wall now. Great Wall of China. It will not allow to come and go, and that current is known as ID, diffusion current. Okay, so it is because of this. So now when this current, when we will have a flow of current, that is electrons, flow of electrons, and hence a current, that current will be known as diffusion, and we have to overcome this barrier. And how we will overcome it? By applying an energy, some potential we will apply, that we will see later on, forward bias and reverse bias. Okay, so this is one current, that is diffusion. Because of this diffusion, you get this depletion region, which is nothing but that respective P and N type, they are depleted of its own charge, and because of that, there is a potential that is established, and it is now acting like a wall, and it will not allow the electrons to flow to the other side, right? There is a control, and very few, if at all, can make it. If the current is in nano ampere, okay, nano means 10 raised to minus 9 of ampere. It is like no current, and when it is operating, when the diode is in forward bias, the current is in the range of milliampere. It's 10 raised to minus 9. Okay, a milli is 10 raised to minus 3 of the ampere. So when it is on and off, the ratio is 1 and then 6 zeros. Okay, so on to off ratio. So it is in milli when it is on, 10 raised to minus 3. When it is off, it is nano. In the hardly negligible current. Okay, nano picoampere. And then there is another kind of current which is flowing. That is IS, we say. It is known, it is the drift current now. This is diffusion, this is drift current. Now what it is, I am just going to explain you. So when there is no voltage applied, and we say in equilibrium, this ID is equal to IS. And drift means, you know, that there is a drift of, you know, in the sea there is a drift. And when there is a drift, everything comes with that. Even whatever the garbage, or when, you know, there is a tsunami and there is a drift, right? Everything goes with that. So now what is that drift? Here also on the same line. See, now drift means what? Now see, as you know that this p-type, it has holes in excess, majority carrier. And similarly for the n-type. That is simple. That is what is for diffusion we saw. But there is something like minority carrier. And in this whole type, there are free holes, but there are very few, but there are electrons. Okay. So this, in the p-type, electrons are the minority carrier, and in the n-type, holes are minority carrier. Okay, so in addition to this majority carrier of the respective p and n type, there are minority carriers also. So for p type, if hole is the majority, electron is the minority carrier. So there will be, okay, if there are 1,000 holes, there will be at least 2-3 electrons free. Do you understand my point?
Yes, ma'am.
Yeah. अभी वो कहाँ से आए? Because of the temperature. It has nothing to do with voltage. Because of the temperature, it will happen that one in the p type, some electron will also get free because of the temperature. I am not talking of 0 degree Kelvin. Huh? So because of the temperature, it will get free and they are known as minority. So 1000 अगर holes है p type में, तो 2-3 electrons भी रह सकते हैं. Because of the temperature, then they will get free. Now, what will happen? That now here in this holes, yeah, I can write. So these electrons are the minority carriers. Here holes are the minority carriers. Okay, just showing you. Now, what will happen? You know that fundamental that like charges, unlike charges attract, like charges repel, right? Unlike charges attract
Yes,
થાય ને
ma'am.
અને like હોય તો repel થાય, બરાબર?
Yes, ma'am.
Yes, ma'am.
Yes. Now, what is happening is that here electron minus side આ minority છે અને અહીંયા plus e minority છે, whole minority છે. So now here this is minority and what happens is you see this is plus. If you talk of this potential here, this is plus, right? This is minus. So now this plus is going to attract this minus and this plus will be attracted by this minus, this potential. Okay, એટલે આ potential એકબીજાને attract કરશે. And then because of that, okay, and see now this is free, moving free here and it will be swapped here. આ swap થઈ જશે અહીંયા because this is attracting now this potential. With this minus, it will be attracted by this potential and it will be swept away. Okay, so it is like drift. A sweep, as a sweep कर this and attract करसे and this will go this side and this will go this side. So now this electron is moving this side, the hole is moving this side, and this potential is helping. But this current is in nanoampere and in equilibrium. Equilibrium means that there is no flow of current from this side to this side here. So that is what, so here equilibrium mean in equilibrium when you say that there is no flow, it is neutralizing. This id is equal to is. Diffusion and drift current are equal in equilibrium. Now let's say what happens if one is little more, because when there is no voltage, there is no current, that means both of this get cancelled out. I nano ma hoy એ cancel થઈ જાય. Okay, so that is what is in equilibrium. Both the currents are equal. But let's say, and then this is the potential, right? In equilibrium, this is negative, positive. But these are electric fields, positive, negative, and they will attract this electric field will attract. Okay, these are all little electric fields. So now what happens that, and then see the equilibrium condition is maintained by the barrier voltage. Okay, so this barrier voltage will maintain this equilibrium. So this barrier voltage is 0 and it will maintain this equilibrium. And let's say that for some reason this id, that is because of the diffusion, that id it is exceeding is because it is exceeding the drift current. Then what will happen? More bound charge will be uncovered on both the sides of the junction. Okay, so now this is the condition, they were equal, but now say that this id is more. So the current because of the id. Okay, they are still in nano only. They are not. It's not working. I mean, it's not on the device. It is in nano, but this diffusion is the electrons are moving this side, and then these electrons. So if this is more, let's say 3 electrons are moving this, and here only 2 are moving. So the id is more. Then because of that, so this is because of diffusion, huh? So physics is different. Understand drift and diffusion. So in this case, when id is more, then what will happen? happen, more bound charge will be uncovered on both the sides of the junction. The depletion layer will widen. Now, when this more electrons are moving this side, so બે અહીંયા આવ્યા અને ત્રણ આમ ગયા તો એક વધ્યું અહીંયા. Okay, so because of that, this will widen. અહીંયા અહીંયા સાઈડ વાળી હશે ને અહીંયાથી અહીંયા આવે છે તો. So this will get widened. This will widen. Similarly, this will widen. So now this is widening. Atli thickness of the it will widen. It will have more negative charges and it will more positive charges. The white things. And because of that, this will increase. This potential will increase. And because that is getting widened. Pardon?
Hello, ma'am. Your
My
voice
volume is
lagging.
gone.
Your voice is
My voice is
lagging in
okay.
between.
it's sometimes lacking.
Lagging. We can't.
Okay, I'll explain you again. Let me do something. શું કરું? See, this is your textbook. Now my voice is okay, or I may change the browser. My voice is okay now?
Yes, ma'am. It is okay now.
Okay. मैं तब तक के जो important है, but I am explaining you and I hope you will understand properly. So I was here. And so now, in equilibrium, you understood. Now, let's say this is getting little more. So, in that case, this depletion layer will widen. Okay. And once this depletion layer is widening, it means that now, equal hoy, but for some reason, let's say ID has gone more. If ID goes more, as I just explained, this depletion region will widen. And the voltage across this V0 will increase. Now this is widening, so more charge negative here, more positive here, and V0 will increase. And then this V0 increase will cause ID to is under, and then until equilibrium is reached. Okay, I increase because of the diffusion, this current will decrease. So the increase thayu tu, okay, it automatically decrease. It is the material property. And then, so this will decrease. So again, that equilibrium will be reached. Or let's take it other way, that ID is less than IS. Okay. So on the other hand, if IS is increased, okay, then ID. Then the amount of uncovered charge will decrease. This is more. Okay. And this potential will decrease on the same line, on the same physics I explained you, right? So here negative charge is the minority. Okay. Here positive charge is the minority. Okay, a minority share. So now here, so this negative will flow here, positive will flow here. Okay, so and but now we are comparing this. So negative એટલે માનો કે આ ત્રણ છે અહીંયા અને અહીંયાથી આ બે જ ઇલેક્ટ્રોન્સ આવે છે because of this diffusion. This is more. So these are 3, this is 2. Okay, so now what is happening? This is recombining with this. Okay, I'm just saying. So this potential will decrease. Thin things. This depletion will even thinner. Okay, so the potential will decrease and it will facilitate. Okay. So now, yeah. So this potential will decrease. This will decrease. Okay, and then once this is decreased further, so what will happen? Then the amount of uncovered charge will decrease. The depletion layer will narrow, and the voltage, that is V0, this will also decrease, and this will cause ID to increase. એટલે હવે આ reduce થઈ ગયું તો ID પાછું increase થઈ જશે. And then ID will increase, right? Because in the second condition we took is 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 more than ID. So if that is the case, then if IS is more, then this depletion will reduce, which in turn will increase ID. એટલે ID ઓછું હતું તો એ વધી જશે. It will be equal to ID will be equal to IS. So under my point to explain you here is under equilibrium, both of these currents are same, and this is like an open circuit. આમાં કોઈ current flow નથી થતો because both of them are same. If for some reason either of them will increase, right, then still it will this property, the physics of this is natural thing. This is the physics, and we are just understanding the physics. We cannot control it. That's what is happening, and it will make it to equilibrium. Okay, so when no potential is applied, this is like an open, there is a potential V0 on equilibrium, and even if it is for some reason on equilibrium, that is either of the current is more, it will come to equilibrium. That is, both the currents are same, and the resultant current is zero because they both are in opposite direction. Then, so now let's say that, so here in equilibrium, as said, it is like an open circuit, both the currents are same. Okay, and there is no potential. But under no potential, because now you have two terminals, you can connect batteries in two ways. Okay, but when there is no battery connected, it is like an open because there is no resultant current flowing. Okay, cancel થઈ જાય છે, it is like an open. But now if you apply battery, then what? Can't you open it? So it is just nothing. It's like a chunk of material just sitting like a rock. We want to use it in a circuit, and what? You need a flow of current. To have a flow of current, you have to connect a battery. Now there are two electrodes, right? The positive one is known as anode, the negative one is known as cathode, right? Plus is anode, and you can connect the batteries because of two terminals. You can connect either way. That is, the positive will be connected to the positive of the battery, and negative will be connected to negative of the battery, or positive will be connected to the negative of the battery, and other way. So two ways you can make a connection. And here what is shown is which bias, this which terminal, this is showing you the battery. Okay, and this little line is positive and the bigger line negative, or what? Which is what terminal here? In a battery, this is positive or negative, chota wala?
Negative.
Okay, very good. So this is negative. So here negative is connected to the positive, and the positive and vice versa. And we say this is reverse biased. And why reverse biased? The name in the reverse biased. Now you have understood this depletion region, that potential, the barrier, it will have some voltage. Now with this kind of battery connection there, what it does, this is, so little one is negative. Okay, and this is positive. Okay, so now this unlike charges will add negative and positive, they will attract. Okay, and because of that, this charges, it will be attracted, and because of that, this, so now this is reducing and this will increase, this depletion region. Okay, so this is getting thicker now, and similarly for this side, this positive and negative, and this will be attracted, this will reduce, and the depletion region will increase. So before it was V0, now it is V0 plus R. So this potential in neutral, it was this much, but now it has increased, and because these are carriers, right? Here it is, so this is negative, here it is all, these are all positive, filled up with this positive, this is negative, and this has increased the width of this. So and all this, if you think in your mind, these are all carriers filled up with negative and positive, and more carriers means more potential, and this potential has gone high, and then that will hardly, because minority, for with minority, even if you have current, it is in nanoampere, it is very low. Okay, and the current in the diode is because of the diffusion, high current. Minority carriers are otherwise also very low, so that current is in nano, almost zero, but because you will have it because of the diffusion. But here this, because now this has increased, it is this wall, It is like a wall which has gone even thicker. It is hard to cross for the electrons and the holes, vice versa. So this will hardly have any flow of electron. Okay, and this is known as reverse bias where no current flows. And this is the physics. And then the other way is you connect this positive with positive, and then this. So when this is connected, this will widen and this will decrease. Okay. So this region which was V0, it is V0 minus Vf, this voltage. And it is like the resistance, the voltage is decreasing. The resistance of this area is also decreasing. It is like very low, and the current can pass, the barriers can easily pass now. They have an energy to cross this wall. Okay, so this electrons, it is reaching, this is whole, it can easily pass now. Without, it's like the barrier is very weak now and it can pass. And this is forward bias region, we say. Okay, and see this potential is decreased. Here it was increased. So it is all understand now. At the end of the day, if you want to understand anything in the whole universe, this whole universe is a sea of electrons. Okay, આપણે દરિયો છે electrons નો. If you get down into the smallest level, and if you want to understand, it is the energy. Okay, so it is the game of energy, and even we as a human, right? It's all energy level. Okay, પછી positive હોય, negative હોય, but it's about energy. And when you talk of, when you bring down everything to the basic component, that is electron, this universe is a sea of electron. And when you talk of electrons, it is the energy that it has. Electrons have different energies. Okay, so here also it's the energy. So the electrons will have some energy, but to cross this barrier energy should be low so that this electron can cross. But if this barrier energy is more, electron can't cross. But if it is low, then electron can cross. So, and another thing, none of the electron in the whole universe is steady. It is always moving. Okay, so the electrons are always moving and they have some more other energy. And it is directly, if you talk in a simple layman way, the electron must have enough energy. That energy is given by this potential. Okay, and that is also controlling this depletion region. Like કાતો આને વધારે એનર્જી આપો, કાતો આને લો કરો, આની એનર્જી લો કરો. This barrier has an energy, right? This potential is the energy. So you know this. Okay, and then let's say if it is remaining this much only, and then still this electrons to move it. Now if you give energy, it will move then fast. It will move in more quantity. Okay, so you have to give some energy so that it will move fast. It will, more number of electrons will move. At the same time, this barrier should also facilitate, and it should not be strong that electrons cannot move. And to do that, you have to bias it in a forward direction, forward bias. ખ્યાલ આવ્યો?
Hello, ma'am.
હા.
Here we say, when we say that the depletion layer widens, does it mean that its width increases or the barrier potential increases?
Both. See, let me get back here. See, અહીંયાથી માનો 20 ઇલેક્ટ્રોન અહીંયા આવીને બેઠા, અહીંયાથી 20 હોલ્સ આવીને બેઠા, તો અહીંયા 20 થયા. અહીંયા I am taking just some quantity to explain you this, what your question. Okay, તો 20 થયા. તો એના માટેનું let's say, because this positive, this is an electric field, positive electric field, little electric field. અને આ 20 નું ભેગું થાય અને આ નેગેટિવ છે, તો આ લિટલ નેગેટિવ ઇલેક્ટ્રિક ફિલ્ડ છે. એટલે એનું પોટેન્શિયલ નેગેટિવ છે અને આ પોઝિટિવ છે. હવે એની જે ઇલેક્ટ્રિક ફિલ્ડ, સો નાઉ ધીસ હોલ્સ આર હિયર એન્ડ ધીસ આર અનકવર્ડ ચાર્જીસ એન્ડ ધીસ ઇલેક્ટ્રોન્સ આર હિયર. એટલે જે રિઝલ્ટન્ટ ઇલેક્ટ્રિક ફિલ્ડ ડેવલપ થશે એ પોઝિટિવ, એનું ડાયરેક્શન આમ હશે. ઓકે, એનું પોટેન્શિયલ V0 છે. ઓકે, હવે આમાં આટલામાં આ 20 ઇલેક્ટ્રોન્સ આવ્યા, આયન્સ આવ્યા અને અહીંયા 20 હોલ્સ આવ્યા. નાવ ઇફ ઇટ ઇઝ વાઇડનિંગ, નાવ મોર કેરિયર્સ આપણે રિવર્સ બાયસ કર્યું હોય તો વાઇડન થાય, બરાબર. તો અહીંયા 20 હતા તો અહીંયા 40 થશે, તો 40 જો થાય તો પછી અહીંયા વધારે જગ્યા જોવે ને એને સમાવવા માટે, અહીંયા 40 થશે તો શું થશે? ઇટ વિલ વાઇડન. It will, if more people, you need a bigger room, right? That
Yes,
way.
ma'am.
So this is flexible. આ wide થશે, આ flexible છે. It depends on the carriers. Okay. So this will widen. And if this is widening, then એનું electric field એ વધશે, એનું potential વધશે. Okay. And if this gets thinner, then 20 માંથી 10 થયા, I 10 થયા. So it gets thinner and the electric field, the potential that it has, can get, you know, you have studied that much કે આપણે 0.4 કે 0.5 વોલ્ટ આપીએ તો પછી એને 0.7 એ કંડક્ટ થશે. ઓકે, so 0.7 એ ઇનાફ એનર્જી છે ફોરવર્ડ બાયસમાં કે this is gone very thin and it is easy to cross and it has enough energy that you will have huge current when it is 0.7. Okay,
Yes.
0.3 ke 0.2, it is still thick enough, the wall is thick enough that in electrons will not, it will be hard for the electrons to cross. And the reverse bias માં તો ક્રોસ જ ન કરી શકે, આમ ગ્રેટ વોલ ઓફ ચાઇના જેવી થઈ ગઈ કે ભાઈ અઘરું છે ક્રોસ કરવું એમ. You understand my point?
Yes, ma'am. Yes, ma'am. And sorry, ma'am. What do we meant by uncovered charges over here?
Yeah. Okay. See, you understand the term recombination? કે ભાઈ,
Yes, ma'am. Yes, ma'am. Yes, ma'am.
yeah. So let me tell you that. See, this is a negative P. So this is this N type, all negative. P type is all positive. Okay. And diffusion, you understand now, moving from higher concentration to lower concentration.
Yes, ma'am.
Okay. Higher concentration to lower concentration. So electrons will move here, this will move here. Now this is negative, this is positive. So initially when they are moving, they will recombine. Means a hole will combine with electron, right? Electron will combine with hole. And it is like a marriage happening. They will combine and that is known as recombination. They will, okay, they will get one. It's combining, recombination. But after they have combined, okay, these are in excess here, and electrons and holes. So these are in excess. So after that, recombination happens and they are covered charges. But after that, these are more in number here, these are more in number here, and then some, so a recombination થઈ ગયું, okay, initially. And then some still electrons are moving because of the diffusion. This is moving here. So few of them got recombined, but there are so many numbers that still you will have this holes this side and then this holes because of the diffusion will come and settle here and this will come and settle here. And there are so many numbers, okay. And these are known as uncovered charges. The ones that combine are covered charges.
Means the holes or electrons that are not recombined are uncovered charges, right? Yes, understood, ma'am. Thank you, ma'am.
Because they are not covered, right? And now here, I mean, so they have already recombination થવાના થઈ ગયું. After that, they are uncovered, and they make, and this is physics, okay. So this is how the nature works, and we cannot control. If you bring P type and N type together, this phenomena will happen. And we have understood, and we cannot create, we are not God that we can make the way we want the things to happen. But we have understood this and we have used this for our benefit in making electronics, and we have to understand the device and we use it. કે આપણને ખબર હોય કે આપણા ભાઈબંધનો નેચર આવો છે તો આપણે એવી રીતે કામ લઈએ, right? So this is the nature of the device that is suited for making electronics, and we make circuits accordingly. Okay?
Yes, ma'am.
Okay, so there is something like Zener diode that I'll cover in my another later lectures. Okay, and there's a Zener diode will do problems, and it is used in your electronics. Very, it's a compulsory thing to be used, and it is for water voltage regulation. Okay, and that I will cover in my next one or two after lectures. But in this line with the diode, in this line with the diode. Let me go ahead because we have still time here. So now we'll start with the diode and its characteristics and how things are. This lecture will be easy, but from the next few you will have to be attentive. And let me go ahead and start with this slide. So this is about linear passive components. We'll start with the basic things first, just to understand some vocabulary. So what are linear passive components? So this slide, just see this for a minute. So they may store or may convert it into heat. So this they store the energy or they may convert it into a heat. So storing energy. Okay. So let's say capacitor. So it will store the energy. Resistor, it will convert it into heat. If a current is passing, it will get heated up. Okay. And they are linear. The current through them is proportional to the voltage. If you draw the IV graph for resistor, it is linear. Okay. So these are linear devices, and these values they remain same. They will not change with the voltage or something. The parameter values does not change with the voltage applied or current passing through them. Their values is same. With the change in voltage, the current will change through them. Okay, so they are static, and so these are static means their values don't change. But on the other hand, how if you compare diode with RLC, okay, it does not store energy. Diode, of course, doesn't store energy, as you can see, right? It is like a switch, and a very small amount of energy is converted into heat. Yes, because the current is passing, and this is again a material. Some will get dissipated, but that is a little amount of that. It is non-linear current through diodes. If you do, if for R and for this, if you go and do this for R voltage and current, you will get this kind of line. Okay, based on the resistors, but the line is a linear one. But in diode, if you this is, let's say this is V and this is I. Okay, so this is your for a resistor or this RLC. It's linear. In a diode, right? You know the diode curve. Everybody knows. So this is in the forward region. It is like this way, and then like this way. So this is not linear. This is non-linear. It's not linearly proportional to right. So it is so called resistance is dynamic. So now this is again I, and if you take a ratio of change in voltage for a change in current, right, you will get R. If you take some right, so here also for this is this the ratio of these two. This is changing. This shows the R, which is changing. So it is dynamic. Okay, so it is changing, so dynamic. In that case, it was static. Everybody knows this diode characteristics. This is the forward region. This is the reverse bias. When you give reverse bias, this is the reverse region of that. And in the reverse bias and forward bias, all these basics now you know. Okay, and this voltage here is known as VZK. Okay, and this is known as the breakdown region, where the diode is the Zener diode. We make it work. I'll take Zener diode later on. We make it work in this breakdown region. Your normal diode gets destroyed. We do not operate it in this region. Otherwise, you will have to throw it out. Okay, so converting nonlinear diode characteristics into simpler diode model. Now see, this thing you should understand as an engineer. model. Now, what is this model? You must have heard of a model. Okay, so these models are nothing but they are equations, IV equation. Now, this is a device which has physics. It is made up of some material. It has some dimensions. So, based on this physics, it will have the IV curve. And it's not only necessary to understand the physics, but you have to have an equation of that. So based on all this mathematics and the physics, there will be an IV equation of the diode. And but now let's say when you are now this diode equations, okay, they give precise current and voltage. For corresponding voltage, it will give you some current precise. And these currents are small in number, and this voltage is right. The It will be operating at, it is on at zero point 0.7 volt, and so that is the diode uh, nature. Okay, and now when you want to make a circuit of a diode, right, it's not that you will pick a diode and you will make something and then you will go to the lab and use all hardware, multimeter and oscilloscope to see and measure. First thing you will do is by pen and paper. Then you will use computer-based tool, simulator, LT Spice that you had used. If things are okay, then connecting in a lab and seeing will not be a problem. It will be as expected. Now, to do all this pen and paper work or a simulation work, you need a set of equations, because that's what, if you want, because pen and paper is okay as an engineer first step, but everything, if this is like one diode, there are like 100 diodes in a circuit, or too many components, right? You have to simulate, and to simulate, your computer will understand what it doesn't know. What is diode? It knows is the IV equation. So every component has an equation, and that equation, set of equations, is known as model. Okay, so and then let's say now when you are doing some, you want to do now this diode applications are as a rectifier, right, where you will have very high voltages also. Okay, so now we are going to study all those circuits slowly. But when you have very high voltages, you don't need very precise, okay, zero point 0.7 drop hua, yeah, zero point 0.5 drop hua, yeah, milliampere current. You don't have to, when you have, let's say, because when our, this in India, these lines are like 230 volt. If you are giving hundreds of volt, right, and you are using diode in such a circuit, we don't care for 1 or 2 volts there. So you will do some crude analysis where that IV equation, for if you want to get some approximate value, some crude value, right? Then you don't have to go for IV equations every time. So we will simplify, we will use some crude way of analysis, a simpler model, which is like very fast, quick kind of thing. Okay. So for that, and then when, if it works good with your simple this thing, then when you apply your equations, it will be 5-10% of variation, not more than that. Okay. So it's not that every time you have to be very precise and use that IV. We can use some simpler models. And for that, we have for diode, one is ideal diode model, we say. Okay. And the other is, we will see linear model. Okay. So in the ideal diode model, the diode characteristic is like this instead of forward bias. Okay. Forward bias, you had like this, and then you had like this, right? So this is here straight line. ये थोड़ा ऊपर चला गया, चले. So but so forget this now. This is the practical thing. But as I said, these are like, this is what, how much volt? This is 0.7, 0.8 volt. Okay, these currents are in milliamp. Now, when you are using this diode where the voltage is very high, we don't need very precise. After that, you can do with very precision. So crude way of analysis, so there we use ideal diode model where the characteristics is like this. That is that at 0 volt it gets on. It is conducting. It is like a wire. Okay, so 0.1 volt, right? It is conducting, and this is short. So it is conducting. It is a short. Okay, and less than 0 volt, it is open. So V less than 0, it is open, and I is equal to 0, right? And when it is greater than 0, it is short, and V is equal to 0 because these 2 points, so whatever the voltage you are giving, these 2 points are the same because it is shorted. So the potential across the diode is 0. Okay, so here we don't take it as zero point 0.7 volt, we take it as 0 volt because, as I said, when you are working with very high voltages, zero point 0.7 is nothing. Okay, so crude way of analysis, a quick way of analysis, and if it works this way, then you can do with precision. So that's okay. So that is one way of doing. So, for example, in this, okay, you have to find out, let's say, using this ideal diode model, I say you find out I current across the loop and the voltage across the diode. Okay, in here 10 volt, 10 volt diode is connected this way here, and here it is connected this way. And ideal diode means the diode is ideal, it will on at 0 volt, and with the voltage and then greater than, of course, 0, and less than 0, it is open. So open and short. So that you have to remember. So here, if you see here, 10 volt here and some resistor, and this is the positive. This, to remember, if you forget this, you know this diode symbol. Okay, this is diode symbol, and this arrow you see here, it is the direction of the current. Okay, and this minus is the minus of the diode, the negative terminal of the diode, minus minus. Okay, so that way you remember this is negative terminal, so this is negative, then it has only two terminals, this will be the positive terminal. This terminal is known as anode. Okay, positive and A. The first A anode is positive, and this is cathode then. So that way you remember the current will flow in this direction because this is the arrow in which the current flows. See, you know that the electrons move from negative potential to this. So electrons move from negative to positive. The current will flow from positive to negative, and this is the direction of the flow of the current. So this is how you remember. Okay, and if you have to find out the current through this, so this is positive. Some drop will happen, but otherwise the voltage that is appearing at the positive terminal of the diode is going to be positive only. So it will be greater than 0, and this is ground, so which is less than, of course, 10 volts. So this terminal of diode is always going to be positive with respect to this terminal, hence this will be forward biased. Using ideal diode model, if it is forward biased, this is like a short, it is like a wire only. Okay, and so this is connected to the ground, means this is a closed loop, and hence current will flow. How much current will flow? I is equal to V, this voltage upon 1K. Okay, so 10 volt upon 1 into 10 cube, तो वो ऊपर जाएगा तो वो मिली एम्प हो जाएगा. So 10 will remain as 10 divided by 1, and in denominator 1K will be 1 milliamp, 10 milliamp it will be. So the current is 10 milliamp, and then the voltage across the diode will be 0 volt because this point and this point are now shorted. So this will be 0 volt. Okay, so that's how you do it. And so this is the current and this is the voltage across the diode using ideal diode. But in reality, there is a zero point 0.7 drop, or it can be 0.72, or it can be 0.65 that you have to do by equation that we will see later on. But that doesn't make much difference, okay, when you are doing a crude analysis, a first stage of analysis. And similarly here also, so this is negative and this is positive, as you can understand. Even if there is some drop, the voltage here will be positive only. And but this is the negative terminal. So negative terminal is more positive with respect to this. So this is reverse biased. And this is like an open circuit. It is open. And when the loop is open, there cannot be any flow of current. So there is no current flowing. right? I is equal to 0. And all this voltage will appear across this diode, right? If you write the loop equation, right, then this voltage plus this voltage plus this voltage is equal to 0. So, and there is no current flowing. So the drop here is 0. So here the drop is 0, right? I is 0. So across resistor there is no voltage drop. So all this voltage drop will be, this diode will be 10 volt. This is negative, here this is positive, this is 10 volt. It will, you write this 10 volt, you write plus this, and then plus this. So this is equal to minus of this. And this is already minus here, so plus 10 volt. This is equal to 0, right? If you write this whole thing, this plus this is 0. That's it. So this is equal to minus of this. And this is already here minus plus, so 10 volt. Shaman Bayu?
Yes, ma'am.
This is all basics only. Remember, once again, last time also I said, again I am telling, you should know Thevenin's, you should know KVL, you should know KCL, how to analyze a network, all these things you should know. But do you understand how things are working? How they are related?
Yes, ma'am.
Okay, if anybody has a query, you type in the chat box. I'll get to this after half an hour. I'm going to create a classroom of yours and my last lecture and my today's lecture, everything I'll put it today only and I'll message you in the group.